Today we're going to talk about the boiling point enhancement, so the boiling point elevation and the freezing point depression of solutions. So let's go ahead and get started with this. So whenever we have a non-volatile solution, what we want to do is we want to compare that to the pure solvent. So we've already seen that is there an increase or a decrease in vapor pressure? Well, on Raoult's law, we talked about previously, there's a decrease. So the boiling point is actually going to increase, and the freezing point is going to decrease. And we are going to answer these two questions and show you quantitatively how to solve for the new boiling point or the new freezing point of a solution compared to that of the pure solvent. And then in turn, what we want you to be able to do is answer what's the effect on the triple point. So if we were to look at a couple examples, what we'll see is that the boiling point and the freezing point change compared to that of pure water, which we're not always guaranteed to deal with pure water, but that's what most of the examples we look at in notes today will look at. If we look at a 1 molal, again we're using molality, not molarity, solution of glucose, what we'll see is the boiling point is no longer 100 degrees Celsius as it was for pure water. And the freezing point is not 0 degrees Celsius. It's negative 1.8 degrees Celsius. But then if we turn around and look at a 1 molal solution of sodium chloride, the boiling point is enhanced further. It's in fact double that of the glucose. And then the freezing point is double that of the glucose. So it's decreased. So why is this further enhanced? So why are the changes further enhanced? Well, let me show you the equations that we're going to use. So we are going to use the boiling point elevation and freezing point depression equations, and we call this delta T sub B, and this is equal to Kb times M, and delta T sub F is the change in freezing point is equal to negative K sub F times M molality. So I want to point out a few things to you. One is previously we looked at the change in boiling point and freezing point of glucose versus sodium chloride, and we saw that for the same concentration, it depended on whether or not there was dissociation. So we are actually going to multiply through by the Van Hoff factor, I. Molality, we should be comfortable with calculating that. So delta TB, or delta T sub F, I'm going to write this as a generic delta T sub I, and we're going to say that the change in temperature is equal to T sub I minus T sub I pure. So this is the temperature of the solution, and this is the temperature of the pure solvent. So we were looking at the difference in the boiling point, so this should end up being a positive value versus a difference in the freezing point, which should end up being a negative value. Now, depending on what source you use, sometimes this negative in the equation may be bundled in with K sub F. Sometimes it may be written over with delta T sub F, but I'm going to use this equation, so then this always holds true, that delta T sub I is equal to the T of the solution minus T of the solvent. So what are Kb and K sub F? Well, Kb and K sub F are the boiling point molal constants and freezing point molal constants. And what we'll see is you have to know the solvent, so you know which constant to use. And these have units of degrees Celsius times kilogram per mole, or degrees Celsius per molal. So you may need these on your homework. On a test, I would give you these values unless you're solving for it, but you can always Google, just watch your units if you're Googling this, because some people might have different units. So let's go ahead and try a few practice problems together. So the first one, what is the molality of an aqueous glucose solution if the boiling point of the solution at 1 atmosphere is 101.27 degrees Celsius? All right, so we're looking for molality. So molality is our unknown. It's glucose, so glucose is a covalent molecule. So we'll assume that it does not dissociate, so our I value is 1. This is the boiling point of the solution. So we can figure out the boiling point of pure water, which is 100 degrees Celsius. So now, let's go ahead and write down our equation. We know that delta T sub B is equal to K sub B times M times I. So we are trying to solve for the molality. So we can rearrange this. So molality is equal to delta T sub B over K sub B times I. We know that delta T sub B is equal to the boiling point of the solution minus the boiling point of the pure water. So we know delta T sub B is equal to 1.27 degrees Celsius. We know that I is 1, and then KB you could look up on your notes or on the internet, and we'd see KB is 0.51 degrees Celsius per molal. So we can start to plug in. Delta T sub B is 1.27 degrees Celsius over K sub B, which is 0.51 degrees Celsius per molal. And then I is just 1. So we'll see our degrees Celsius cancels out. And molality is the denominator of the denominator, which means it's in the numerator. So whenever we plug this in, we'll end up with molality is equal to 2.5 molal. And recall that molality is, in fact, moles of solute over kilograms of solvent. So it will really help if you make a list of all of the variables, figure out what you know, what you don't know, and then rearrange the equation for your unknown, and then go ahead and plug that in and solve for your unknown. So let's do one more example. In this one, we want to find delta T sub F. So we want to determine the freezing point of a solution made from 3 kilograms of water and 3.5 moles of sodium chloride. And we want to assume complete ionization. Okay, well, since we're looking for a freezing point, we know our equation will be delta T sub F is equal to negative K sub F times M times I. So what we want to do is we actually want to solve for delta T sub F first before we start to find the freezing point of the solution. So let's make a list of what we know. K sub F, because this is dissolved in water, is 1.86 degrees Celsius per molal. Our molality is moles of solute over kilograms of solvent. Well, we have 3.5 moles of solute over 3 kilograms of solvent. And then our Van Hoff factor, since we're assuming complete dissociation, is 2. So what we can do is we can go ahead and plug in. So delta T sub F is equal, don't forget your negative sign, negative 1.86 degrees Celsius per molal times the molality, which is 3.5 over 3.0 times I, which is 2. So when we plug this in, delta T sub F is equal to negative 4.3 degrees Celsius. Now recall that delta T sub F will be equal to the freezing point of our solution minus the freezing point of our pure solvent. So here, delta T sub F is negative 4.3 degrees Celsius. We're looking for the freezing point of our solution, and the freezing point of pure water is 0 degrees Celsius. Well, if you add 0 to both sides, what we'll end up finding is the freezing point of our solution is equal to negative 4.3 degrees Celsius. So one of the things that you should watch for is if you don't have water as your solvent, and it will be explicitly stated within the question that it's not water, this value will be different. The freezing point or the boiling point of the pure solvent will be different. your K sub F will also be different as well. It will not be negative 1.86. This is just for water. So make sure you're paying attention to this and look up anything in the table that you need.